Assalamualaikum and good afternoon to everyone. My name is Nuratika Shahira binti Uyo, who do the introduction part for experiment 4, which is minor losses in pipes. We from group 5. My group members is Nurul Hazmira Hani binti Haznan, and next is Nurul Nadrah binti Zulhairi, and the last one is Nurul Natasha binti Norzain. Now I will explain about the objective for this experiment. The objective for this experiment is to determine the loss coefficient KL value and minor head loss HLM in pipe components or fittings for different water flow rates, pipe diameters and pipe bend. To do this experiment, we have the theory for this experiment, which is the theory is the flow in piping system at different flow rates may be required to pass through a variety of fitting, bends, or abrupt change in area. Additional head loss called as the minor head loss HLM are encountered primarily as a result of flow separation. By simplifying the Bernoulli equation between 2 points for the horizontal, Z1 is equal to Z2 for the pipe. The pressure loss, we use the P capital P, and total head loss HLT could be determined as follow our next equation. This slide show many equations. All of these equations we need to simplify to determine the HLM minor head loss and calculate the KL value. KL value is the coefficient of the loss coefficient. Okay. Now from this 5 equations we can simplify where KL is coefficient associated with HLM dimensionless and HLM is minor head loss. As you can see, from equation 4, we can get the HLM equals to KL V square divided to G, and KL equals to 2G times which HLM divided V square. For the equation 1, show that the total head loss equals to major head loss plus minor head loss. So from these 5 equations, we simplify. So the next slide is, next slide have show the meaning of all the symbols that we use in the formula, and where P1 minus P2 equals to pressure drops between 2 points and the unit is Pascal. Rho equals to density of flowing medium kg meter cubic. G is gravity constant 9.81 ms negative 2. V1 minus V2, where the change of velocity of flowing medium from points 1 to points 2 in the unit ms. HLT is total head loss, the unit is meter. HL is major head loss, unit also the meter. F is the coefficient of pipe friction, so it's from the dimensionless, so it is dimensionless. And the L is equals is the length of the pipe in the unit meter. Di is the internal diameter of pipe, also unit meter. V, capital V for HL, speed of flowing medium for the test pipe. And the HLM, we know that minor head loss, the unit also meter. V for HLM, speed of flowing medium in the vicinity where the minor loss occur. And the KL we need to determine. So KL is loss coefficient associated with HLM, which is KL is dimensionless, and last one is H1 minus H2. H1 minus H2 is the differential height in manometer between points 1 and point 2, and the unit is meter. So the theory for this experiment, to determine the KL value, the value of KL is heavily dependent on geometry of component and fluid properties. We include the RE. Mathematically, it can be expressed like this. So in most practical cases, the KL for components are a function of geometry only. In this experiment, the KL value and the HLM in pipes for different water flow rates, pipe diameter, and pipe bands will be determined. The description related to each of test geometrical is as follows. First, sudden expansion or enlargement and sudden contraction. For the next slide, we have the figure that show the loss coefficient of flow through sudden area change. We can get KF value for flows through a sudden expansion or enlargement and contraction from continuity for equation 7 and momentum for equation 8. So as you can see that we have equation 7 and equation 8. So for the next slide, for those equation can be rearranged to give the theoretical KL for sudden expansion enlargement. So KL equals to 1 minus AI1 divided AI2 and square. Whereas the theoretical KL for sudden contraction can be expressed as KL equals to 1 minus A12 divided AI1 and square. So for the second test, is the elbows, pipe bands, and pipe branch. The valve of HLM and KL for the flow involving pipe components fitting, such as elbows, pipe bands, and pipe branch, could be determined experimentally using the equation 3 to equation 5. So it's follow the equation that we rearrange above. An example of typical values of KL for pipe component fittings are shown at the next slide. So this is my last slide. So this is my last slide. This slide shows the typical value of KL for pipe components or fitting. That's all from me. Thank you.
Hi, my name is Nurul Hazmirahani binti Hasnan. So I will present about the methodology part. So first of all, this is the apparatus used in the experiment 4. So this is the set that we use that consists of tested pipe section, outlet valve, inlet valve, 2 tube manometer, and the manometer tube at the bottom. Okay, so we go straight to the methodology. So basically what we have done for this experiment, firstly, the direction of water inflow and outflow for the tested pipe section were determined. Second, the inlet valve of the tested pipe were fully open and the inlet valve were closed. The pump was turned on and the outlet valve were slowly opened until maximum for a while to remove any air bubbles that exist in the tested pipe section. Number 4, the inlet flowing pressure, which we denote as H1, and the outlet pressure, which we denote as H2, for the tested pipe was identified, then the manometer tubes from those H1 and H2 of the tested pipe were connected to the two-tube manometer at the bottom. Number 5, the values of H1 and H2 at two-tube manometer were recorded in millimeter unit. Then the actual water flow rate was determined by recording the time taken to collect 3 liters volume of water at the tank. Next, number 7, the step is the opening of the outlet valve were reduced, and steps 5 to 6 were repeated for 5 different values of Q at actual. And then after finish, the manometer tubes were removed, first to avoid bubble in the tube. With pump in running condition, steps 1 until 6 for the other tested pipe section were repeated, meaning that we substitute the pipe with another type of pipe, and then we repeat the steps again. And for the last one, after finish, all the manometer tubes from the system were removed, the inlet and outlet valves were fully closed, and the pump and the main switch were turned off.
Okay, hi, Assalamualaikum warahmatullahi wabarakatuh. So, in this experiment, Tasha will present what result. As we can see in table 1, it is the data for sudden enlargement and sudden contraction. So, we need to find the Q actual and delta H. To find the Q actual, we need to volume collected divided by time. And then we get the Q actual. While to find the delta H, H1 minus with H2. So, same goes to table 2, which is data for elbow and pipe bend. We have three types of pipe, which is angle 90 degree, bend 90 degree, and angle 45 degree. So for table 3 is data for pipe branches. We have two types, which is Y type and T type. We still use the same formula as previous one. In this calculation, we want to find the loss coefficient and minor losses. So first of all, we need to find the inner diameter first. So we need to find the inner diameter first by using the formula outer diameter 1 minus width 2 times width thickness. So we need to find the inner diameter 1 and inner diameter 2. After we find the inner diameter 1 and inner diameter 2, we need to find the area 1 and area 2 by using formula pi times width inner diameter power of 2 divided by 4. So after we find the area 1 and area 2, we need to find the loss coefficient using formula 1 minus area 1 divided by area 2 power of 2. So next we need to calculate the V1 and V2 by using formula 4 times with Q actual divided by pi times with diameter 1 for V1 and diameter 2 for V2. So we find the Reynolds number by using formula V1 times D1 divided by V, which is V at temperature 36 degree is 7.095 times 10 power of negative 7. So we find F using losses formula, which is 0.316 divided by 0.316 divided by square root power of 4 times with Reynolds number. So after we find the F, we can find the minor losses by using formula V1 minus V2 power of 2 divided by 2G. So the loss coefficient for sudden enlargement and sudden contraction is 0.4117. So we use the same formula for sudden enlargement and sudden contraction. Next. Pipe, which is 90 angle, 90 bend, and 45 angle, is a bit different calculation compared to the previous one because we don't need to calculate the loss coefficient because we can take directly from the table. So we can calculate the minor losses by using formula loss coefficient times with V power of square divided by 2G. So for Reynolds number and F, we need to calculate using the formula from previous one. Same goes to Y type and T type. We still use the same formula as 90 band, 90 angle and 45 angle. That's all from me. Thank you. Thank you.
My name is Nurul Nadra binti Zulkhairi and I will present the discussion. The first part of this discussion will be talking about the effect of different water flow rates, pipe diameters, and pipe bands on the value of loss coefficient. So the first one is water flow rate. Water flow rate is inversely proportional to the square of water velocity. It is directly proportional to the water velocity. When the water flows in high speed, the water flow rate will become larger and lowering the value of the loss coefficient. Second, pipe diameters. Pipe diameters is an internal cross-sectional area of the pipe that is directly depends on its internal diameter. So when water flow rate in a straight pipe is constant, the area increase with diameter, which cause the water velocity decrease and water flow rate will become larger. So the last one is the pipe band. The longer the pipe bending, the larger the radius of the value of water flow rate. So the value of water flow rate also decreases with the angle of bending. The value of water flow rate for Triton pipe connection is higher than flank pipe connection. So for the second part in the discussion, we'll be discussing about the error or accuracy in experimental data, also the recommendation to improve the existing result. So the first error, we found that the presence of air bubble in the tube and pipe. For the second error, the unstable flow rate of water which causes water level into tube manometer cannot be calibrated. It fluctuated heavily. So the third error will be the parallax error due to incorrect position of eyes to reading the scale. So for the recommendation for the first error will be we need to make sure that there's no presence of air bubble by flowing the water in pipe and secure the tightness of all interface before taking the reading. The second recommendation for the second error, repeat the experiments few times and get more than one measurement for each reading and find the average to get the accurate value. So the recommendation for error 3, the parallax error can be minimized by viewing the reading at eye level at the meniscus. So the eye level must be perpendicular to the scale that needs to be read. So the conclusion is, in this experiment, show that minor losses really play a major role on fluid mechanics and movement. It needs to be considered when transporting fluid is present so that the amount of waste energy can be reduced. This experiment also helped us to learn the minor losses in depth by mastering their calculation and factors. The objective to determine loss coefficient and head loss in this pipe for different water flow rate, pipe diameter, and pipe band also achieved. That's all from us. Thank you.